On a quiet trajectory far from Earth, an object has started to awaken far earlier than expected. The first traces appeared when it was still more than 3.5 astronomical units away from the Sun, a distance where most comets remain silent and frozen. Instead, this one began releasing water in steady, powerful streams. Its coma glowed a deep, almost unnatural green, not from dust but from cyanogen and atomic nickel. Observatories across the world logged the same thing, an energy surge with no clear trigger, a burst that should not be happening this far out. This isn't 3I Atlas, but its behaviour is forcing scientists to revisit everything they thought they understood about the quiet phase of approaching visitors. It mirrors the same pattern that first made 3I Atlas impossible to ignore, and this new object is on a fast track toward its closest encounter with Earth in just days. The anomaly is not just its speed or brightness, it is the way it is lighting up, the chemistry in its wake, and the growing suspicion that this isn't a typical solar system comet. What is coming next may redefine how we classify interstellar objects entirely. The first hint arrived as a faint green shimmer captured by mid-range observatories. At a distance where most comets are still locked in silence, this object began to stir. 3.5 astronomical units from the Sun, far beyond the orbit where water ice normally begins to sublimate, its coma expanded like a slow, deliberate breath. It wasn't subtle. The rise in brightness outpaced any known curve for this stage of approach. Instead of the usual dim flicker of a cold traveller, the signal flared as if something deep inside the nucleus had crossed an invisible threshold. Telescopes on multiple continents confirmed it. The initial suspicion of instrumentation error faded as the same readings repeated night after night. A dense, expanding envelope surrounded the nucleus, illuminated not just by reflected sunlight, but by an internal process that seemed to feed on itself. Astronomers began running models to explain how this much water could be released so far from the warmth of the Sun. None of the early results fit standard cometary behaviour. Then came the spectral signatures. The coma wasn't dominated by water vapour alone. It was rich in cyanogen, which often signals deep chemical layers breaking open. More striking was the unmistakable presence of atomic nickel, a marker rarely seen this early, if at all, in solar system comets. Usually nickel appears later, after more intense heating. Here, it was showing up in strength before the object had even crossed the critical boundary where such emissions normally begin. This timing was more than unusual, it was unprecedented. If the models are correct, the outgassing began when the object was still in a zone where energy from the Sun should have been too weak to trigger such behaviour. That alone would make it a major event. But the green coma, dominated by these volatile compounds, points to something deeper happening inside, a layered structure that allows trapped gases to escape in powerful bursts once pressure builds past a threshold. Observers are describing it as a preemptive bloom, the kind of activity usually seen much later in a comet's journey. That has triggered one of the most intense early monitoring campaigns in recent years. Every hour matters now, because the evolution of this outburst will reveal whether this is a simple natural anomaly or a sign of something much stranger. As the data accumulates, patterns begin to emerge. The energy isn't random. It follows a rhythm. Small fluctuations superimposed on a steady upward climb, as though something inside is breathing in time with its rotation. That regularity suggests the surface isn't just venting at random. It may be structured, fractured pathways or porous channels directing the gas outward with remarkable consistency. Meanwhile, the object itself is closing in. In less than a week, it reaches a point where its coma will be visible to mid-level amateur telescopes. That's when the story will stop being confined to quiet observatories and will become part of the global sky-watching record. This early surge, already stronger than many expected at perihelion, is reshaping how scientists view the timeline of such events. But this is just the beginning, because what surrounds the object is not just a faint halo, it is a glowing green shell, carrying a chemical fingerprint that breaks the pattern of solar system comets entirely. For most comets, the first visible sign of awakening is a pale, hazy tail that builds slowly as sunlight warms their frozen cores. But this one announced itself differently. Its coma isn't the soft white of dust and vapour we've come to expect. It's an intense, unmistakable green. That colour isn't just beautiful, it's forensic evidence. It reveals the chemistry inside the object, the pressure building within its nucleus, and the way it interacts with solar radiation long before most comets even stir. This green glow comes from a specific combination of compounds, cyanogen gas and atomic nickel, both of which are notoriously hard to detect this far from the Sun. Under normal conditions, cyanogen only becomes abundant once a comet is closer, warmed enough to free deep trapped volatiles. Nickel typically appears only after sustained heating, when the outer crust cracks and heavier elements begin to vent from subsurface layers. Here, both signals appeared early and strong, lighting the coma like a beacon. From the first spectral readings, researchers understood they were seeing something highly irregular. Cyanogen can be a trace component of a comet's gas envelope, but rarely the dominant one at this stage. Its early release suggests a layered nucleus with volatile-rich material lying just beneath the surface, pressurized by internal heating and triggered by even minimal solar input. Nickel's presence is even harder to explain. Unlike lighter molecules, it doesn't simply sublimate. It requires either grain lofting, where gas rushing through pores lifts microscopic particles into space, or direct liberation from unstable mineral structures. Either way, the implication is the same. This object isn't behaving like something forged in the inner reaches of our own solar system. The brightness curve has been equally revealing. Typical comets brighten at a steady pace that roughly follows their distance from the Sun. This object isn't following that rule. It's brightening at a superlinear rate, meaning it's outpacing its expected curve by a significant margin. That's not just a quirk, it's a red flag. It indicates that something about its composition or structure is amplifying the sublimation process as it approaches. Think of it less like a block of ice slowly melting in the sun, and more like a pressure valve snapping open in bursts, releasing gas and dust in escalating waves. Observatories in both hemispheres have reported the same phenomenon, the coma expanding in size and density at an accelerated pace. But what stands out most is the glow itself. When captured in longer exposures, the coma's inner region shows a tight, bright green core that fades gradually into a larger, more diffuse halo. That layered structure is critical. It suggests there are two active zones, an inner one dominated by heavy volatile release, and an outer one shaped by how solar radiation breaks down these compounds and scatters them through the surrounding space. Cyanogen plays a key role here. When it interacts with ultraviolet light, it fluoresces in green, giving the coma its characteristic hue. But the strength of that signal is astonishing for this distance. Scientists studying archived spectra from previous comets, including those that passed much closer to the Sun, have noted that this object's cyanogen band is several times stronger than expected. That intensity isn't random noise, it's the signature of an active, chemically rich environment unlike anything in recent memory. Then there's the nickel. Its spectral lines are sharper, less diffuse, and unusually pure. That clarity suggests a concentrated source of nickel-bearing grains being lifted directly into the coma. On Earth, nickel is a marker of high-temperature processes, volcanic vents, smelting, meteoritic cores. In comets, its early appearance is rare. Some astronomers have proposed that the nickel may be trapped within mineral grains formed in an environment with low iron content. That would make this object chemically distinct from most comets we've catalogued. The contrast between nickel and iron is especially telling. Iron, usually abundant in these kinds of objects, is notably absent from the early readings. If this holds, it points to a formation history tied to a low metallicity region, perhaps an older part of the galaxy where heavier elements were scarce during the object's birth. That aligns with growing evidence that not all interstellar visitors are chemically alike. Some may come from ancient stellar nurseries where conditions were radically different from those that shaped our own solar system. The halo itself is also structurally odd. Unlike most comets, which show asymmetric coma patterns as jets and vents direct gas unevenly, this one's glow is surprisingly uniform. There are faint hints of jets, but the overall profile looks smooth, almost engineered in its balance. That doesn't mean it's artificial, but it does mean the internal structure may be unusually porous and evenly layered, allowing gases to escape across a broad surface rather than through a few concentrated vents. Such behaviour has profound implications. If early, evenly distributed outgassing is tied to internal architecture, this could help explain why the brightening curve is accelerating so smoothly. Instead of waiting to cross an activity threshold closer to the Sun, the object has already entered a stable outburst phase, one that may continue uninterrupted as it nears Earth. That makes it a perfect natural laboratory. Every change in brightness, every shift in spectral lines, gives scientists clues about what lies beneath its surface. And yet, there's another layer to this story. Some in the scientific community caution against drawing quick conclusions. Just because the object shows unusual behaviour doesn't mean it's unprecedented. A handful of comets have shown early cyanogen activity before, though never quite this strong. Others have exhibited smooth coma structures, though not at this distance. The difference here is in the scale and timing. This isn't a faint anomaly at the edges of detectability, it's a full-throated signal, visible and measurable with clarity. In the coming days, as it moves steadily closer to the inner solar system, these properties are expected to intensify. That means more data, more light curves, and more pressure to interpret what exactly is happening. If the cyanogen levels spike further and the nickel signature remains clean while iron remains absent, it could confirm a working theory already taking shape, that this object is a visitor from outside our system, carrying a chemical fingerprint shaped by an older, quieter corner of the galaxy. But the green halo isn't just a scientific curiosity, it's a warning flag for what's to come. Because early cyanogen activity often hints at volatile-rich interiors, the later stages of this object's approach could be violent. Jets could erupt without warning, the coma could expand rapidly, and the brightness could surge unpredictably. That volatility is what makes interstellar visitors both fascinating and dangerous to predict. Astronomers are now racing to coordinate telescope networks worldwide, aiming to capture every stage of the coma's evolution. Even amateur observers are being brought into the fold. Coordinated citizen science can reveal rapid changes that large observatories, limited by scheduling, might miss. The green halo has already drawn their eyes. Soon, it may offer the first public glimpse of a truly alien chemical signature glowing in our night sky. This is where the narrative begins to shift. What started as a distant, silent traveller has turned into a luminous, active body whose chemical fingerprint does not match our expectations. The coma isn't just bright. It's broadcasting information about its structure, composition, and possibly its origin story. And this is only the surface. Beneath that green glow lies a physical mechanism, one that is feeding this eruption with quiet precision. Understanding it means looking deeper into how gas and dust interact within a porous layered body hurtling toward the sun. From the outside, the glowing halo looks smooth, almost serene, but what drives it from within is anything but. Deep inside this object, pressure is building, layer by layer, grain by grain, as volatile gases trapped in a porous structure begin to wake up. Unlike a solid block of ice, a porous comet nucleus can behave more like a breathing organism. The heat from the sun creeps in slowly, slipping through channels and fractures, finding weak points in the crust. At first it's subtle, microscopic grains loosen, tiny vents open. But once the pressure crosses a hidden threshold, something remarkable happens. The entire system begins to feed on itself. Scientists call this process a sublimation feedback loop. When trapped gases start to escape, they don't just drift away. Their rapid expansion scours out the surrounding material, enlarging the pores and accelerating the flow. The more gas escapes, the more the structure opens. The more it opens, the more heat penetrates. And with more heat, even deeper layers begin to sublimate. This cycle can transform a quiet, distant object into a roaring engine of activity long before it's supposed to light up. For most comets, this process doesn't fully kick in until they are much closer to the sun. But this object is behaving as if its surface is already primed for it, like a pressure cooker with thin walls, ready to burst with minimal external push. That's why astronomers are paying such close attention to its current behaviour. Early activation at this scale isn't just a curiosity, it can rewrite our understanding of how interstellar objects interact with solar energy. The internal structure likely plays a decisive role. Imagine layers of dust and ice stacked loosely, with pockets of volatile compounds trapped between them. Over time, as the object drifts through interstellar space, micrometeor impacts and cosmic rays create a labyrinth of microfractures. When it finally approaches a star, even faint warmth slips through these cracks, reaching deep reservoirs of gas. The result isn't a gradual melting, it's a chain reaction. Thermal models suggest that once this chain begins, the rate of outgassing no longer depends solely on distance from the sun. Instead, it becomes self-sustaining, at least for a time. The energy from escaping gas helps expose new surfaces, and those new surfaces release even more. It's like a quiet detonation stretched over weeks, controlled, steady, but unstoppable once it begins. This is what makes the object's superlinear brightening curves so significant. It's the signature of a feedback system in motion. If it were just a patch of surface warming, the brightness would follow a predictable slope. But here, the curve is bending upward, as if driven by a hidden engine. Observers describe it as a curve with intent, and this engine doesn't need high temperatures to run. Volatiles like cyanogen and carbon dioxide can activate far earlier than water ice, making them ideal for early-stage outbursts. Once they start flowing, they lift grains from the nucleus, including nickel-bearing particles, and throw them into the coma, where they reflect sunlight and create the distinctive glow. The pressure inside may also be uneven, producing pulses as vents open and reseal in cycles tied to the object's slow rotation. This rhythmic venting is already appearing in the data. Nightly observations show tiny oscillations in brightness, not random noise, but a steady pattern. These variations likely trace the rotation of the nucleus as different sections come into sunlight and then drift back into shadow. Every turn exposes a fresh patch, triggers a new pulse, and adds another layer to the feedback loop. For mission planners and astronomers, these pulses are gold. They provide a natural way to map the object's shape, spin, and internal activity without sending a spacecraft. If this pattern holds as it approaches Earth, it could give us one of the clearest timelines ever recorded of a volatile-driven feedback process at work in real time. But this mechanism also carries risk. A feedback loop can accelerate unpredictably. One small fracture can cascade into larger structural failure, unleashing massive jets or even fragmenting part of the nucleus. When pressure builds faster than the crust can release it, eruptions follow. And because this object is active much farther out than usual, those eruptions could happen before scientists have fully modelled its behaviour. There's another layer here, one that connects this feedback loop to the broader interstellar puzzle. If the nucleus is more porous and volatile-rich than typical comets, that could explain not only its early activation but also its likely origin. Objects formed in colder, lower metallicity environments tend to trap more volatile compounds in their structure. Over millions of years, those compounds stay locked away until a nearby star offers just enough warmth to set them free. The green halo isn't just a pretty sight, it's a direct expression of that distant birth environment. In that sense, what we're seeing right now may be less about what's happening here, near Earth, and more about what happened long ago, far away. Every jet, every flare of brightness, is a fossilized memory being reawakened. But the feedback loop doesn't end here. The gas escaping isn't just carrying nickel grains and volatile molecules with it, it's doing something stranger, creating a chemical imbalance. Nickel is flooding out, iron is not. And that contradiction is about to take center stage. Because in the world of cometary science, nickel without iron is like thunder without lightning. It simply doesn't happen under normal conditions. And yet, here it is, clear, bright, and measurable. The data first appeared as a faint but clear signature on a spectrograph. A sharp emission line, bright and narrow, standing out against the broader background. Nickel. It wasn't weak or ambiguous. It was prominent, clean, and unmistakable. And almost immediately, researchers noticed what wasn't there. Iron. In nearly every known comet, nickel and iron appear together, their spectral lines rising in tandem as heat unlocks the deep layers of the nucleus. But this object has broken that pairing wide open. At first, some teams assumed it was a calibration issue. Instruments can misread faint lines, especially when background light interferes. But as more telescopes pointed at the object from different continents and different instruments, the pattern didn't change. Nickel remained strong, iron remained absent. The signal was consistent across nights, angles, and atmospheric conditions. This wasn't noise, it was a signature, and it was strange. Nickel and iron are siblings in most cometary material. They form under similar conditions, often in the same mineral structures, and are released together as the nucleus warms. For nickel to appear without iron means something deeper, a fundamental difference in the object's chemical makeup or the physical way it's venting its material. That single observation has already ignited debates in research circles. One camp argues that this is a structural effect. In their view, the object might be rich in nickel-bearing grains that are more loosely bound than iron-rich material. As gas surges through its porous layers, it lifts the lighter, more fragile nickel grains first, leaving iron locked deeper inside. If true, iron might appear later in the approach, when the surface warms enough to tear open the heavier mineral layers. The other camp believes it's not just a matter of timing, they point to formation history. The absence of iron could be a relic of where this object was born. In parts of the galaxy with lower metallicity, older, quieter regions where heavy elements are scarce, objects can form with unusual chemical balances. In that environment, nickel could dominate while iron is comparatively rare. If this interpretation holds, we're not just looking at an unusual comet, we're looking at an object with a fingerprint that reaches across interstellar space. Nickel's behaviour here is telling. In a typical comet, its emission builds gradually as the object nears the Sun, peaking later in the journey. Here it surged early, strong and stable. That suggests nickel isn't buried deep beneath a thick crust. It's woven into the near-surface layers, ready to be lofted into space by even mild outgassing. It also suggests the structure of the nucleus may be layered differently than we're used to, less like a solid rock and more like a sponge packed with volatile grains. As the green halo thickens, telescopes are now picking up subtle shifts in the nickel signal itself. Instead of fluctuating wildly, it remains surprisingly steady, with only minor variations tied to the object's slow rotation. That stability means something important. Nickel is being released not through violent jets, but through a broad, sustained flow. It's as though the entire surface is bleeding it out evenly, without the chaos that usually accompanies metal release in comets. That even distribution also explains why the coma looks so smooth. Nickel grains are microscopic, and when they're released gradually across the surface, they create a dense but stable cloud around the nucleus. This contributes to the uniform green glow. No sharp flares, no patchy bursts, just a continuous, eerie radiance that has already drawn comparisons to a lantern in deep space. Meanwhile, iron's absence is becoming more than just a curiosity. It's now a dividing line. If iron fails to appear in the next phase of its approach, it will confirm that this object's chemistry isn't just odd, it's alien. And not alien in the sensational sense, but in the very literal way scientists use the word, formed in a place fundamentally different from our own. A place where the balance of heavy elements is skewed, shaped by stars that burned and died long before our sun existed. This matters for more than academic reasons. The iron-to-nickel ratio is one of the quiet cornerstones of how astronomers classify comets and asteroids. It helps trace their origins, their age, and the processes that shaped them. A clear, persistent imbalance forces a rewrite of those categories. It suggests that the catalogue of interstellar visitors may be far more diverse than anyone assumed. Already, parallels are being drawn to previous anomalies. When Oumuamua raced through the solar system, its reflectivity and acceleration defied simple classification. When Borisov passed through, its chemical composition hinted at unfamiliar formation processes. But this object is different. It's offering a direct chemical signature, clear and measurable, long before its closest approach. It's not just behaving strangely, it's speaking a different chemical language altogether. There's another layer of intrigue in the nickel data. Some researchers suspect that nickel may be acting as a tracer for other hidden volatiles. The grains could be hitchhiking on invisible flows of carbon dioxide or other exotic compounds carried upward in a kind of steady wind. If so, that means the nickel signal isn't just a curiosity, it's a map of the object's inner structure, telling us where the gas is moving and how the layers are connected. It's also worth noting what this means for observation strategy. Iron's absence makes this object stand out sharply against the background of known comets, allowing it to be tracked more precisely with spectral instruments. It's as though the sky has handed astronomers a clean, bright marker to follow, one that cuts through the usual noise. But this anomaly, this nickel without iron, also points towards something more fundamental. The volatile chemistry driving this display isn't typical. And the next lines on the spectrum are already pointing to the culprit. Not water, not silicate dust, but carbon dioxide. This is where the story deepens. Because the timing and the chemistry suggest that this object isn't being driven by the usual sequence of volatiles we see in comets born here. It's running on a different fuel, one that speaks to its distant cold birthplace. When most comets awaken, their first fuel is water. Solar heat seeps into the crust, the ice begins to sublimate, and a thin veil of vapour expands outward. But this object is running on something else. The first strong volatile signal coming from its coma is carbon dioxide, not water. That single fact turns the usual story upside down. Carbon dioxide behaves very differently from water ice. It requires far less heat to sublimate, which means it can start driving out gassing at distances where water remains frozen solid. This explains the early surge at more than 3 astronomical units, but it also tells us something more fundamental. The surface and near-subsurface layers of this object are dominated by compounds we don't typically see as primary drivers in solar system comets. The entire timeline of its activity is shifted forward. What usually happens near the inner solar system is happening now, far away. This early carbon dioxide dominance creates a unique kind of coma. Water-driven comas often grow slowly and irregularly, fed by jets that burst open once enough energy builds up. Carbon dioxide, by contrast, can flow steadily at lower temperatures, producing a broad, stable envelope. That steady flow explains why the green halo formed so quickly and why it has maintained its shape without the violent flares usually associated with early comet activity. But the chemistry reveals more than just timing. Carbon dioxide is often trapped in the deeper layers of solar system comets, buried beneath water ice and dust. For it to be the first volatile out of the gate here, it must lie close to the surface or in porous channels that allow it to escape easily. That suggests the nucleus was formed in an environment colder and more volatile-rich than what we see in the inner solar system, a place where carbon dioxide condensed as one of the first building blocks, rather than being locked away beneath heavier layers. This is consistent with what many astronomers have theorized about interstellar objects. Unlike solar system comets, which formed in the gravitational cradle of a young star, interstellar bodies may have assembled in the outskirts of older, colder systems. Their chemistry reflects that difference. Instead of being dominated by water and silicate dust, they can be saturated with more fragile compounds like carbon dioxide, carbon monoxide, and cyanogen. This makes them volatile time capsules, preserving chemical conditions from environments humanity has never directly sampled. The transition from carbon dioxide to water dominance in a normal comet is gradual and predictable. As it moves closer to the Sun, carbon dioxide leads the charge, then water takes over as the primary driver of activity. But in this case, carbon dioxide is releasing with such force that it may remain dominant much longer. That changes everything about how scientists are modelling the object's behaviour. The strength of this signal is forcing teams to adjust their timelines. They expected water signatures to appear first and gradually increase. Instead, they are observing a surge of carbon dioxide strong enough to shape the coma and define its chemical character weeks ahead of schedule. Water is present, but it is playing catch-up. That has practical consequences. The size of the coma, its stability, and the shape of its halo all depend on which volatile is driving the outgassing. Carbon dioxide is more mobile at lower temperatures, meaning the coma can expand more evenly and steadily. It also carries grains differently, allowing fine particles like nickel to remain suspended for long periods without being overwhelmed by heavier dust from water-driven eruptions. This chemical balance explains the extraordinary clarity of the spectral lines being recorded. It also fits with another anomaly. The brightness increase isn't chaotic, it follows a smooth curve, one that mirrors theoretical models of carbon dioxide-dominated sublimation. That stability is one of the reasons scientists believe this object might give them the cleanest look yet at interstellar comet behaviour. Without the unpredictable eruptions of water jets, the coma acts like a calm laboratory, revealing its chemistry layer by layer. There's another reason why this matters. In the context of interstellar chemistry, carbon dioxide dominance can hint at the kind of star system this object came from. Systems formed around older, metal-poor stars tend to produce icy bodies with a different balance of volatiles. If the iron-to-nickel imbalance and carbon dioxide signature both hold, they may point to a single story, an object forged far away in an ancient, cold, low-metallicity neighbourhood of the galaxy. Scientists are already preparing to test this hypothesis. As the object approaches the Sun, they expect the relative levels of carbon dioxide and water to shift in a measurable way. If the carbon dioxide remains in control longer than expected, it will confirm that the upper layers are unusually rich in these volatile ices. If water suddenly surges, it will suggest a layered structure, with a buried water ice reservoir waiting to take over. Either way, the result will help map its internal composition with astonishing precision, all from the comfort of Earth-bound observatories. But the significance goes beyond chemistry. This object's early carbon dioxide release echoes a growing pattern seen in the last two interstellar visitors. Oumuamua defied classification with its strange acceleration. Borisov surprised scientists with its unusual volatile mix. Now, this object is carrying that pattern forward, adding another piece to the puzzle. Each of these arrivals is a messenger. Together they suggest that interstellar visitors are not rare anomalies, but a diverse population with shared traits that differ sharply from anything born in our own solar system. And as we gather more data, these visitors are starting to sketch the outline of something bigger, a map of how worlds form across the galaxy. Carbon dioxide isn't the headline most people expect when they hear about a comet or an approaching interstellar body, but for scientists, this early volatile dominance is the key. It's the mechanism that set this entire chain of anomalies in motion. The early activation, the green halo, the nickel surge, the absence of iron. And this is where the story starts to echo previous mysteries. Because this isn't the first time an object has broken our expectations. It fits into a timeline that began years ago with two other messengers from deep space. Each arrival begins the same way, a point of light, faint against the star field, flagged by automated survey telescopes. At first, they look like any other comet. But then the anomalies begin to stack. The world saw this pattern before, once in 2017 and again in 2019. The first was a strangely shaped object tumbling through the solar system at impossible speed. The second was a volatile-rich comet from far beyond our neighbourhood, and now this third visitor carries echoes of both, while adding its own signature to the growing puzzle. The first of these was Oumuamua. It entered our system on a hyperbolic trajectory, travelling too fast to have originated here. At first it was thought to be a typical asteroid, but it lacked a coma, showed no visible outgassing, and yet displayed subtle acceleration that couldn't be explained by gravity alone. It was small, elongated, and eerily quiet. That silence left a vacuum, one that theories rushed to fill. Natural explanations competed with more exotic ones, but the real message of Oumuamua was clear. Interstellar objects were not hypothetical anymore. They were here. Then came to I/Borisov. Discovered 2 years later, it behaved more like a traditional comet, but even it carried chemical surprises. Its coma was rich in carbon monoxide and other volatiles uncommon in solar system comets. Its activity level was extraordinary, and it showed no sign of slowing as it approached perihelion. Where Oumuamua was silent and inert, Borisov was loud and active, glowing brighter and brighter, revealing a chemistry forged in colder, stranger places. This new object, now entering the inner solar system, isn't a simple repeat of either case. It's something in between. Like Borisov, it's volatile-rich, already active at a distance where most comets sleep. Like Oumuamua, it seems chemically distinct, carrying a fingerprint that doesn't match local patterns. But it's not subtle about it. From the moment it crossed into observational range, its behaviour has been loud, green, and persistent. It's writing its own chapter in this unfolding narrative. The comparison is more than academic. Each of these objects tells us something different about the environments that produce interstellar wanderers. Oumuamua, with its silence and strange acceleration, hinted at unusual physical structure. Perhaps a fragment, perhaps a remnant of something larger. Borisov, with its active coma and volatile mix, spoke of icy regions colder and more volatile-rich than our Kuiper belt. This newcomer, with its carbon dioxide dominance, nickel flare, and iron silence may be pointing to yet another kind of birthplace, one shaped by low metallicity and fragile chemistry. What makes the timing significant is how quickly these arrivals are stacking up. For most of human history, interstellar visitors were the stuff of theory. Oumuamua changed that. Borisov confirmed it wasn't a fluke, and now, only a few years later, we're facing another one. And this time, the science teams are ready. Automated survey systems, spectral networks, and citizen astronomers are mobilizing faster than ever before. Where Oumuamua slipped through with limited data, this object will not. The early spectral work alone already exceeds what was gathered on Borisov in its first weeks. Instruments are trained on it night after night, feeding into shared databases, creating a living timeline of its evolution. Unlike the first two visitors, which left more questions than answers, this one may give us the clearest glimpse yet into the diversity of interstellar bodies. But this isn't just about collecting facts. The comparisons matter because they expose a pattern, a quiet, emerging truth about our galaxy. The differences between these objects are as revealing as their similarities. All three exhibit chemical and physical behaviours unlike most solar system comets. All three arrived on hyperbolic paths, untouched by the gravitational shaping of our Sun. And all three show evidence of volatile chemistry that hints at environments colder, older, or chemically poorer than our own. Taken together, they suggest that the interstellar population isn't an oddity. It's a constant presence, a quiet stream of travellers crossing through our system on their way to nowhere in particular. We simply didn't have the eyes to see them before. Now, with deeper surveys and better instruments, the picture is filling in. This growing pattern also forces a shift in how scientists think. If three objects so different from typical comets have arrived in such a short time, the diversity out there must be staggering. That raises deeper questions. How many kinds of icy bodies roam between the stars? How many of them are older than our solar system itself? How many carry chemical records of stellar nurseries long extinguished? For this latest visitor, the pattern is already emerging in real time. Its carbon dioxide dominance, nickel surge, and green coma are not isolated curiosities. They fit into a broader arc, a story of objects born in places we've never seen, crossing light years to deliver their signatures to our doorstep. The quiet truth beneath all the noise is that these objects aren't just astronomical events. They're time capsules. They carry inside them the fingerprints of distant star systems, locked in ice and dust since long before Earth existed. And with every new arrival, that archive grows richer. Scientists are no longer asking if there's a pattern. They're asking how deep it goes, how many signatures will align, how many trajectories will cross our skies in the years to come, how many clues will quietly pass through before we truly grasp what they're telling us. This is where the investigation begins to change shape. It's no longer just about one object. It's about understanding how it fits into a growing constellation of anomalies. One arrival may be coincidence. Three may be the start of a new map. And this map is beginning to point towards something larger, something structured, a pattern that can be tested, measured, and challenged with real data. And that brings us to the next step of the story. The turning point where theories stop being stories and become experiments. When a single event defies expectations, scientists call it an anomaly. When it happens twice, they start asking questions. When it happens 3 times in less than a decade, it's no longer a footnote, it's a signal. Interstellar visitors are no longer rare celestial surprises. They're becoming a pattern, a quiet thread weaving through modern astronomy, each arrival leaving behind chemical breadcrumbs, pointing towards something larger than any single object. The pieces of this puzzle stretch back to the moment Oumuamua slipped past the Sun. Its speed, shape, and unexplained acceleration forced the world to acknowledge that interstellar bodies weren't just theoretical. Then came Borisov, showing us a volatile-rich chemistry that felt alien yet strangely consistent. Now, this third object is doing something subtler and far more instructive, revealing a kind of structured behaviour that can be measured. If Oumuamua was a mystery and Borisov was a message, this new object feels like the beginning of a language. Across observatories, researchers are noticing the same thing. These visitors share unusual timelines. They activate early, carry volatile chemistries uncommon in the inner solar system, and behave as if they were built under entirely different stellar conditions. Their light curves rise differently. Their spectral signatures point to compounds that don't normally dominate activity in solar system comets. And perhaps most importantly, they each carry the fingerprint of environments colder, older, or less chemically rich than the place we call home. That fingerprint has 3 repeating elements. The first is early activation far from the Sun, well beyond the distance where typical comets begin to wake. The second is chemical asymmetry, such as strong carbon compounds or metallic ratios that defy local norms. The third is stability, a smoothness in their activity curves that suggests a different kind of internal structure. Taken together, these traits form the foundation of what some astronomers are now calling the visitor profile. It's not a formal category yet, but the term is gaining traction. A visitor profile is a set of physical and chemical behaviours that help distinguish interstellar bodies from solar system comets long before their orbits are fully mapped. This is a critical shift. Until now, astronomers have had to rely primarily on trajectory to identify interstellar visitors. If an object's orbit is hyperbolic, it's a candidate, but trajectory alone comes late in the discovery timeline. By the time we confirm it, the object may already be fading. With a visitor profile, the signature can be spotted earlier, sometimes weeks earlier, giving scientists time to coordinate observation campaigns, allocate telescope time, and, crucially, consider missions. That's why this third object matters so much. It's giving the world a clear, sustained view of what that profile looks like in real time. The early carbon dioxide surge, the persistent nickel without iron, the stable green halo, these aren't random curiosities. They are signals, markers that can be recognized in future objects. And patterns like this don't just guide observation, they shape theory. The chemical fingerprint aligns with models that describe formation in ancient low metallicity star systems. These are regions of the galaxy where heavy elements were scarce, where ices formed early and volatile compounds dominated. If that's true, it means we're not just seeing stray rocks, we're seeing fragments of stellar nurseries that formed long before the Sun. Each visitor carries the memory of a different neighbourhood in the galaxy, like postcards from places we'll never visit. The growing frequency of these detections also raises deeper questions. Are we seeing more of these visitors simply because our telescopes are improving, or is something changing in the interstellar flow around us? Space is not empty. Our solar system moves through the galaxy, crossing streams of material shaped by stellar winds, long-dead stars and gravitational tides. Perhaps we are entering a region dense with ancient fragments. Perhaps they've always been here, and only now are we finally able to see them. The implication is profound. If this pattern continues, interstellar objects might not just be occasional events. They could be constant, silent travelers passing through every year, unnoticed for centuries. Some might be faint and inert like Oumuamua, others might blaze green like this newcomer, but all of them are pieces of the same puzzle, a galactic migration of frozen fragments that has been happening since long before humans learned to look up. This pattern also forces a rethink of risk and opportunity. These objects aren't just scientific curiosities. Their unpredictable behaviour, volatile content, and sometimes close approaches make them both a source of data and a potential hazard. Their arrival paths are harder to predict because they don't orbit the Sun in closed loops. They appear, flare, and vanish back into interstellar space. Yet within that uncertainty lies opportunity. If scientists can identify these visitor profiles earlier, they can prepare. Rapid response telescope networks can be aligned. Space agencies can analyse launch windows. Small intercept missions, something once considered science fiction, could become real. An interstellar visitor is not bound to return, which means the first pass is also the last. And this is where the story starts to turn. For the first time, the global scientific community isn't just observing, it's beginning to organise. Networks once built for near-Earth asteroid tracking are being adapted to flag early signs of visitors. Spectral databases are being designed to search for the unique fingerprints, cyanogen surges, carbon dioxide dominance, metallic anomalies, that distinguish these objects from anything homegrown. Patterns, when recognised, can be transformed into predictions, and predictions can be tested. In the coming weeks, scientists expect this object to cross several critical thresholds, changes in light curve, volatile ratios and coma expansion that will either confirm or challenge the visitor profile. Every observation sharpens the pattern. Every anomaly fits into a larger structure. We are no longer watching a single traveller. We are watching a fleet, one arrival at a time. But recognising a pattern is only the first step. The next is testing it. And this object, perhaps more than any before, offers a rare chance to do exactly that. Scientists have already drawn their lines in the sand, clear, falsifiable predictions that will either hold or fall as the days unfold. Patterns only become science when they can be tested. For this new visitor, the predictions have already been written. They are not vague guesses or distant speculations. They are sharp, measurable triggers, moments in its evolution that will either confirm or fracture the theories now forming around it. In that sense, this object isn't just a discovery. It's a live experiment unfolding in the night sky. The first set of triggers focuses on its volatile chemistry. Right now, carbon dioxide is the dominant driver. If the models are correct, as the object moves closer to the Sun, the balance should shift. Water ice should begin to sublimate more aggressively, changing the coma's structure and the composition of the gas envelope. If that shift happens slowly and unevenly, it would resemble a solar system comet. But if it doesn't, If carbon dioxide remains firmly in control, that will confirm the idea of a surface and subsurface layered unlike anything born in our neighbourhood. The second trigger lies in its metallic signature. So far, the object has displayed a clear, strong nickel line with no iron. Some researchers believe iron will eventually emerge as the surface heats and deeper layers are exposed. Others argue it will not, because the iron simply isn't there. That's not a philosophical debate, it's a binary outcome. Either the iron appears in the coming days or it doesn't. If it does, we're looking at a structurally unusual but still somewhat familiar body. If it doesn't, we're looking at something fundamentally foreign, the chemical memory of a place forged in different cosmic conditions. The third trigger involves its light curve. So far, the brightening has followed a smooth, accelerating slope that matches theoretical models of carbon dioxide-dominated sublimation. If this curve suddenly spikes, it would suggest a hidden reservoir of volatiles bursting free. If it holds steady, it supports the idea of a layered but stable nucleus. And if it flattens earlier than expected, it could signal a structural change, the collapse of vents, the sealing of fractures, or a sudden stabilization. Each outcome would reveal a different aspect of the object's physical makeup. Beyond chemistry and light, there are rotational triggers too. Subtle periodic fluctuations have already hinted at a slow, steady rotation. But as it nears the sun, heating could cause vents to shift or expand, creating new pulses. If the rhythm of these fluctuations changes dramatically, it would mean the internal pressure has reached a tipping point. If it remains constant, that implies a more uniform, porous structure than most comets, a rare kind of mechanical stability. All of these triggers share one important trait. They are falsifiable. They can prove theories wrong. In a field often filled with speculation, that makes this object uniquely valuable. It isn't just an enigma to be admired, it's a testbed, a way to separate romantic ideas about interstellar visitors from the hard data that will shape the next decade of discovery. For the teams watching it, every night matters. The window is short. Once the object swings behind the sun, there will be days, perhaps weeks, when direct observation is impossible. That gap will decide how much of the story is captured and how much slips away. The predictions must rise or fall before the light is lost. This is why networks across the globe are mobilizing in a way they didn't during the first two interstellar encounters. With Oumuamua, by the time its strange acceleration was confirmed, the object was already fading. With Borisov, much of the early activity was missed. This time, scientists are not just observing, they are racing the clock. Multiple research teams have publicly stated their expectations. One expects iron to appear 3 weeks before perihelion. Another believes it won't appear at all. Some predict a sudden flare as carbon dioxide gives way to buried water ice. Others expect a steady climb with no surprises. These aren't just technical forecasts. They are lines drawn in real time, waiting to be tested by the cosmos. Falsifiable predictions are the foundation of real discovery. If the object behaves as expected, it will strengthen the emerging visitor profile and help refine models for future encounters. If it does something entirely different, it will force a rewrite, and that rewrite may be even more valuable. Either way, knowledge expands. But this race isn't happening in hidden laboratories or behind closed doors. For the first time, amateur astronomers, backyard observatories, and citizen scientists are part of the prediction game. Their data, often collected from rooftops, fields, and makeshift observatories, is already helping to track brightness fluctuations in real time. Some of the clearest early readings didn't come from major observatories at all. They came from people simply pointing their telescopes at the night sky. That distributed network is critical. Major observatories can't track the object around the clock. They're bound by weather, schedules, and priorities. Citizen observers fill the gaps, creating an unbroken timeline that can reveal subtle triggers before they grow large enough to dominate. In this way, the object isn't just testing scientific models, it's testing how the world observes. Every flare of green light, every quiet shift in brightness, every new line in the spectrum either confirms or challenges a theory. These aren't abstract numbers in a database. They're the fingerprints of a real body moving through our neighbourhood at interstellar speed, and the fact that anyone with a telescope can be part of that test is quietly transforming astronomy itself. The next phase of this story will not belong to one team or one institution. It will belong to thousands of eyes watching from around the world. The first two interstellar visitors caught the scientific community off guard. By the time networks were fully mobilized, Oumuamua was already vanishing into the dark, and Borisov was well past its most revealing phase. This time, the story is different. From the moment the new object's green halo flared in the data streams, a wave of coordinated observation spread outward, not just from professional observatories, but from thousands of backyard telescopes, remote stations, and small skywatching networks around the world. This is where modern astronomy has quietly changed. A decade ago, such an event would have been documented primarily through a handful of major facilities. Now, citizen astronomers play a central role in building the observational timeline. They can capture gaps between scheduled observations, track changes hour by hour, and provide ground truth from multiple locations at once. What once required international committees can now unfold organically, almost like a living organism reacting to a stimulus in real time. Many of the early brightness fluctuations from this object were first detected not by flagship observatories, but by amateur stations in rural areas where light pollution is minimal. Some of these observers operate high-grade telescopes from their backyards, linked through cloud platforms that allow their data to sync into shared global archives. Within hours, small clusters of observers were confirming the same microvariations in the light curve. This kind of global synchronization was unthinkable during Oumuamua's passage. Citizen contributions go beyond simple measurements. They shape the narrative of the event itself. Small observatories can track how the coma expands, how the color changes with each night, how the halo interacts with solar wind. That constant watchfulness turns an unpredictable visitor into something mapped almost in real time. It's also changing how scientists think about strategy. Major telescopes can't be everywhere, and their time is limited, but thousands of citizen observers, scattered across continents, can form a net that doesn't sleep. When one sky is covered in cloud, another is clear. When one hemisphere rotates into day, another slips into night. This network can record behavior that might otherwise be lost forever. And right now, every piece of data matters. This object is entering a volatile phase. Its carbon dioxide surge is expected to evolve. Its nickel signature may shift. New jets might open as it warms. Capturing those changes in real time could determine whether the theories surrounding its structure hold or collapse. What makes this moment different is that the data doesn't have to travel slowly through institutional pipelines. It flows through online platforms, open forums, and real-time dashboards where professionals and amateurs compare readings, adjust exposure settings, refine trajectories, and flag anomalies. In many ways, it mirrors the early days of weather forecasting, when scattered observers became a global network. Some of the clearest long-exposure images of the green halo have already come from individuals. The sharpest early spectrum reading of its nickel line came from a small observatory tucked into a mountain valley, far from any urban light. It was confirmed hours later by a major facility, proof that the citizen network is not just supplementary but foundational. This democratization of discovery comes with another advantage: resilience. Large observatories can be disrupted by scheduling, weather, or technical limits. A distributed network is harder to silence. When something happens suddenly, a flare, a structural collapse, a color shift, the odds that someone somewhere is watching are higher than ever. Astronomy is no longer just a science conducted by institutions. It's becoming a shared human effort. A rare object crosses the solar system, and within minutes people across the globe point their instruments upward. They are no longer passive witnesses, they are part of the experiment. As the visitor nears its closest approach, this global net will become even more crucial. If the light curve surges or collapses, if jets erupt, if the nickel signal fractures or iron finally appears, those first moments will likely be caught by someone in a backyard before they're confirmed by a major observatory. Those snapshots will become permanent parts of the historical record. For many of these observers, this isn't just data. It's a once-in-a-lifetime encounter, a chance to contribute to the understanding of something that came from beyond our star, something that will never return. Their images, their logs, their measurements, they are pieces of a collective story that will outlast the visitor itself. But all this coordination and attention isn't only about gathering data, it's about preparing for what might come next. Because if the trajectory holds and the activity continues, a narrow launch window will soon open, one that could allow humanity to meet this traveller not just with telescopes, but with a machine. Every interstellar visitor is a once-and-forever opportunity. Unlike comets born in the solar system, these objects will never return. They don't orbit the sun, they pass through, offer a brief moment of visibility, and vanish back into the darkness between stars. That makes each encounter a test, not just of science, but of our ability to act. This is why every hour now matters. As the object draws closer, a narrow window is opening. If a spacecraft were to be launched within this period, it could intercept the visitor at close range. Such an encounter would turn speculation into direct evidence. No telescope, no matter how advanced, can fully reveal the structure of a comet's interior or the exact layering of its volatiles. But a probe, even a small one, could. This idea isn't science fiction anymore. It's already being discussed in real mission studies. The timing, however, is unforgiving. Interstellar visitors move fast, their orbits are steep and fleeting. To catch this object, a launch would need to be prepared not months from now, but almost immediately. Several rapid intercept mission concepts already exist. They were drafted in the aftermath of Oumuamua, refined after Borisov, and are now being dusted off again. These designs focus on lightweight, high-velocity probes that can be deployed quickly and accelerated along precise trajectories. The technical details are ambitious, but not impossible. One concept involves using existing launch vehicles paired with a small spacecraft capable of executing a fast burn to match part of the object's trajectory. Another involves slingshot maneuvers around Earth or Venus to give the probe the speed it needs without excessive fuel. A third concept relies on pre-positioned platforms that could launch interceptors within days of detection. The goal wouldn't be to land or match velocity perfectly. That would require monumental energy. Instead, the mission would aim for a high-speed flyby, a brief but transformative encounter. Instruments would map the coma, measure the gas composition, photograph the nucleus, and collect in situ data as the spacecraft races past. Even a few seconds of close-range observations could yield insights no ground-based telescope can match. This possibility wasn't realistic during Oumuamua's approach. Detection came too late, and the technology wasn't ready. By Borisov's arrival, mission designs existed, but timelines were still too slow. Now, the landscape is different. The growing expectation that more of these visitors will arrive has pushed agencies and private groups to think faster, build smaller, and act sooner. The early detection of this object, combined with the clear visitor profile it's displaying, has given mission planners a luxury they've never had before: lead time. That doesn't mean the task is simple. Launching a probe on such short notice would require bending existing schedules, reallocating resources, and pushing infrastructure to its limits. But for the first time, the window is open early enough to make that conversation real. Around the world, the discussions are happening quietly but seriously. Some are focused on the scientific return, direct samples of gas composition, clear images of a nucleus forged beyond our system, confirmation of volatile layering unlike anything seen before. Others are focused on what this means strategically, the ability to respond to fast-moving objects of any kind, whether natural or artificial. And then there's the human side of the equation. The idea of sending a machine to meet an object born in another star system carries a weight beyond data. It's not just about knowing, it's about reaching out across the void, even if only for seconds, to study something that has crossed light years to pass by our home. But the window is narrow and the opportunity will not wait. Once the object swings behind the sun, the trajectory will shift, the energy demands will rise, and the practical chance to intercept it will close. Mission teams are working with that hard reality. Decisions made in the next few weeks will determine whether this becomes the third great missed opportunity, or the first successful interception in human history. And behind the technical calculations, there's a deeper conversation. One about why these visitors are becoming more visible, more frequent, and more chemically distinct. Patterns can lead to missions, but they can also lead to questions we're not entirely prepared to answer. Every great discovery carries a shadow, the assumptions we project onto it. When something extraordinary appears, the mind races to make sense of it. It reaches for patterns, analogies, familiar shapes, and in that rush, even the most disciplined observers can fall into a trap: the quiet pull of expectation. That's what scientists are now trying to guard against. This object has already triggered intense speculation. Its early activation, its carbon dioxide dominance, the nickel without iron, the luminous green coma, it all fits a story that seems almost too clean. Observers see the same pattern that emerged with Oumuamua and Borisov and begin to expect the rest of the script to follow, but space doesn't obey human narratives. The danger lies in what psychologists and data analysts alike call confirmation bias. Once a theory gains traction, evidence is unconsciously sorted into fits and doesn't fit. Patterns are sharpened, outliers are softened, and anomalies that contradict the story are quietly ignored. It's not intentional, it's human. But it can bend the shape of science itself. This is not a hypothetical risk. Oumuamua was a textbook case. Its odd acceleration and strange shape led to a torrent of speculation, some scientific, some not. Every new observation was interpreted through the lens of what people already believed. When it didn't behave like a comet, it was called something else entirely. When Borisov appeared, many expected it to follow the same path, and for some it did, even when its behaviour clearly differed. The team observing this third visitor is trying to break that cycle. They know how easy it is to connect the dots too early, to build a story that reality then refuses to follow. That's why they've structured their predictions as hard, falsifiable triggers rather than narratives. Either iron will appear or it won't. Either the light curve will break its smooth climb or it won't. Either carbon dioxide will remain dominant or water will take over. These are not matters of interpretation. They are facts that will be revealed in time. But bias creeps in through more than just scientific debate. Public fascination amplifies it. Images of the green halo have spread quickly. So have the rumours that it's artificial, that it's unlike anything ever seen, that it's part of a larger hidden pattern. Some of these claims echo past narratives almost word for word. The repetition is striking, and it shows how quickly information turns into mythology. The professional community faces a delicate balance. On one hand, they need to communicate the object's uniqueness honestly. The nickel signature, the volatile dominance, the timing. On the other, they must resist turning unknowns into stories before the evidence speaks. That's why most official statements so far have been careful, restrained, almost deliberately quiet. Bias doesn't just distort public perception, it can influence how data is collected. If observers expect a spike in brightness, they may interpret minor fluctuations as signs of that spike. If they expect iron to emerge, they may keep looking in the same spectral band, missing something else entirely. That's why global teams are distributing their efforts, sharing responsibilities across multiple observatories, and letting independent groups verify results before conclusions are drawn. This kind of deliberate skepticism isn't cynicism, it's survival. Science advances through doubt, through the willingness to be wrong. If the visitor behaves exactly as predicted, the emerging profile grows stronger. If it doesn't, then the real story is deeper than anyone realized. And the only way to find it is to stay open to what the data actually says. It's worth remembering that this object, like Oumuamua and Borisov before it, is not trying to tell a story. It has no intention. It's just passing through, carrying with it the quiet imprint of the place where it was born. The story will be written not by what people hope to find, but by what the cosmos reveals when the glow is stripped down to hard numbers. As the intercept window narrows and the object's activity builds, the risk of bias grows stronger. Every new fluctuation, every green flare, every slight shift in brightness becomes a moment for interpretation. And this is exactly when science must be most disciplined. Because behind the noise of expectation lies the real prize. The object itself, untouched, unbent by human narrative. When something crosses the solar system from the deep beyond, it carries no map, no message, no language. What it does carry is its chemistry, the volatile mix it exhales, the metallic balance in its coma, the way it reacts to sunlight. These are quiet signatures of the place where it was born. This is how scientists are trying to listen to the new visitor now. Not through myth, not through speculation, but through the language written into its own material. The first and loudest whisper is the carbon dioxide. Its dominance points to an environment much colder than where most solar system comets formed. In our system, water ice is king. It drives the activity as comets warm. But for this visitor, carbon dioxide isn't buried deep beneath layers of other ices. It's right near the surface, ready to sublimate long before the sun's heat intensifies. That suggests it was born in a region where carbon dioxide condensed early, where temperatures were so low that fragile volatiles remained at the surface for eons. The The second whisper comes from the nickel without iron. That imbalance isn't just a laboratory curiosity, it's a fingerprint. In many ancient star-forming regions, particularly those far from the bustling spiral arms, the heavy elements that make up rocky worlds like ours were scarce. Nickel and iron, forged in the deaths of stars, weren't evenly distributed. Some nurseries received one, not the other. If this object truly lacks iron but bleeds nickel in steady streams, it may have come from one of these older, quieter neighbourhoods of the galaxy, places that formed their first small, icy worlds billions of years before our sun existed. Then there's the behaviour itself, the early awakening, the smooth brightening, the stable coma. These traits all point to a nucleus with a layered but evenly porous structure. That means it wasn't battered by frequent collisions like many solar system comets. It's old, yes, but it's also intact, a quiet traveller that has likely wandered for millions, perhaps hundreds of millions of years. Its surface isn't young, it's ancient and preserved. Astronomers studying galactic dynamics have long known that our solar system isn't isolated. It moves through the galaxy, drifting through regions shaped by the remnants of other star systems. Those systems form, live, die, and scatter their debris across interstellar space. Most of that debris is small and invisible, grains of dust carried on the tides between stars. But sometimes a survivor drifts across our path, a fragment of a star system that's long gone. This visitor fits that description perfectly. It is not a newcomer from a nearby star, it's a remnant of something older, a piece of a system that may have burned out before life emerged on Earth. Its composition is like an accent in a foreign language, familiar enough to understand, different enough to know it comes from elsewhere. There are hints that its structure may be even more complex. Early models suggest it may have spent much of its existence drifting through cold interstellar clouds, untouched by any star. That prolonged deep freeze would explain why its volatiles are still so fresh. It hasn't been cooked, melted, or eroded by repeated perihelion passages. It's a time capsule, nearly pristine, from an age and a place no one can name. Some scientists quietly admit that this is the most intriguing aspect of the entire encounter. The object doesn't just tell us where it's been, it hints at when. If the nickel-to-ion ratio is confirmed to be extreme, if the volatile balance remains stable, this could be one of the oldest intact interstellar fragments ever recorded. That kind of material is priceless. It's a physical relic of a galaxy before our own star was even born. But whispers can only tell us so much. A comet doesn't leave a label on its surface. Its birthplace can only be inferred from patterns, metallic ratios, volatile timelines, structural behaviour. Still, these clues are powerful. Taken together, they paint a picture of a distant, cold, low metallicity environment, a cradle of ices and dust that existed in a quieter corner of the galaxy, possibly before the sun lit up the solar system. And now, against all odds, that fragment is passing through our sky. For a few short weeks, it lets us read its chemical history before disappearing forever. That is the quiet gift of interstellar visitors. They do not speak loudly, they don't answer questions directly, but they leave hints scattered in their glow for anyone patient enough to listen. This is why the final days before its perihelion are so critical. What happens next may sharpen those whispers into something closer to a voice, or it may erase them, hidden behind the sun until it's too late to observe. And that moment is nearly here. The object is closing in. Earth is rotating toward its closest watch. The green halo is intensifying, and the volatile balance is nearing a turning point. In a matter of days, the encounter peaks. Everything has been building to this. For weeks, the object has been brightening, venting its strange cocktail of volatiles and broadcasting the chemical story of its distant origin. Now, its closest approach is no longer a distant date on a chart. It's imminent. Within days, its green halo will reach peak brightness. Its activity will hit maximum intensity. And the chance to study it in detail, to listen to its quiet alien signature, will narrow to a thin window before it swings behind the sun and vanishes into the black. For the scientific community, this week is not routine. It's a sprint. Schedules are shifting. Observation priorities are being rewritten in real time. Telescopes that normally chase distant galaxies are turning toward a single luminous visitor, racing past the inner solar system. Networks that have been tracking its light curve since the first shimmer are now locked into continuous monitoring, hour after hour. The predictions are on the table. Will carbon dioxide remain the dominant driver all the way through perihelion? Or will buried water ice finally seize control and reshape the coma? Will iron emerge at last? Or will the nickel signal hold its eerie isolation? Will the brightness surge suddenly? A violent jet eruption? A structural fracture? Or will it keep rising with its slow, unnerving steadiness? None of these questions can be answered in advance. They will be answered in the sky, in real time, as thousands of eyes watch from Earth. The night sky itself will change in subtle ways as the object moves closer. The coma, already broad and luminous, will swell further, casting a green haze around its core in long exposures. Fainter telescopes will pick it up more easily now, turning passive stargazers into witnesses. The rotation-driven pulses may become sharper, exposing fractures or internal vents that were too faint to detect before. And if a sudden flare happens, the kind that can double brightness in hours, it will be caught by amateurs and professionals alike. Mission planners are watching just as closely. If an intercept launch were ever to happen, this week would define whether it remains a technical fantasy or becomes a historical decision. Even without a probe, coordinated radar sweeps and spectral bursts are planned to make the most of this rare alignment. It's the kind of all-hands moment that only happens a few times in a generation. But not all of this is scientific. There's something quiet, almost unsettling, about how quickly the object has become part of global awareness. Its image, the green halo, the elongated glow, the steady approach, has appeared on news outlets, scientific bulletins, and amateur astronomy forums across continents. People who never cared about interstellar objects are watching the sky, waiting. That attention carries weight. It sharpens the sense that this isn't just another comet. It's a traveller from somewhere else, and this week is the only time humanity will ever see it up close. A century from now, its name will sit next to Oumuamua and Borisov in textbooks, and for a handful of nights we are the generation standing beneath its light. The trajectory models show how brief that light will be. In less than 10 days, the object will swing behind the sun, invisible to Earth. By the time it emerges again, the brightness will likely fade. Jets will cool, the coma will disperse, and the chance to read its volatile signature clearly will be gone. All of the evidence scientists need to test their predictions lives in this narrow window. But this is also when surprises happen. Oumuamua accelerated unexpectedly after it passed perihelion. Borisov held its activity longer than models predicted. This new object may follow the script, or it may tear it apart. A single unexpected surge could rewrite the timeline. A structural collapse could reveal layers hidden since the dawn of its creation. Citizen observers, amateur networks, university telescopes, and major institutions are now synchronized like never before. It's a living, breathing global effort, a network of thousands turning their instruments toward a single green flare. If a surge happens in the middle of the night in one hemisphere, another will record it in real time on the other side of the world. This visitor will not vanish unseen. And yet, beneath all the scientific preparation, there's a strange emotional undercurrent. The quiet recognition that this is an encounter with something that began far away and long ago. A piece of an ancient, silent world will glide past us and be gone. We will measure it, photograph it, analyze it, but we will never see it again. While all eyes are fixed on the luminous green halo of this newcomer, something quieter is happening behind the scenes. It isn't the only object moving through the inner solar system. In the background, 3i Atlas itself continues its strange evolution, a slow, deliberate spectacle unfolding in parallel. This silent competition between two celestial visitors isn't a collision or a chase. It's a race for attention, for telescope time, for the brief sliver of human focus that can capture their secrets before they disappear. Atlas has been at the centre of astronomical fascination for months, its own volatile behaviour and compositional oddities making it one of the most closely watched interstellar objects of recent memory. Its nickel-rich emissions, its superlinear brightening, and its uncanny rotational surges have already challenged assumptions. It isn't fading into irrelevance now. If anything, it's entering its own critical phase, just as this new traveller reaches peak activity. That overlap is unprecedented. Two active, volatile-rich interstellar visitors lighting up the solar system at once. One trailing a green coma that ignites the night, the other quietly building energy as it nears its maneuver window. Telescopes, mission planners, and observation networks are now being forced to split their gaze between two anomalies instead of one. Every hour spent on one object is an hour not spent on the other, and every new data stream deepens the tension over where the scientific effort should focus. Some argue that Atlas, with its long history of observation, remains the higher priority. It has already revealed too many puzzles to turn away now, and its perihelion window is critical. Others counter that the newcomer offers something Atlas cannot: a clean, pristine chemical fingerprint, still in its first active surge, untouched by months of monitoring fatigue. In a field where opportunities vanish into deep space in a matter of weeks, this kind of competition isn't philosophical, it's practical. Behind these debates, telescopes are quietly rebalancing their schedules. Observation time that was locked in months ago is being renegotiated. Robotic survey telescopes that normally follow Atlas every night are alternating targets. Space agencies are evaluating whether limited tracking assets should follow both trajectories or commit to one. It's not about preference, it's about capacity. There's only so much sky one network can cover at once, but competition isn't always bad. It can sharpen focus. It can drive better science. The dual presence of Atlas and this newcomer allows for something no single object could provide: comparison. Two different interstellar visitors, moving through similar solar conditions at nearly the same time, offer an unprecedented natural experiment. If their light curves diverge, that tells us something about structure. If their volatile signatures evolve differently, that tells us something about origin. If they share traits despite their differences, that suggests deeper patterns at work. Already, subtle contrasts are emerging. Atlas is emitting in nickel and cyanogen with a slow, rhythmic pulse, while the newcomer's carbon dioxide surge is smooth, almost unnervingly steady. Atlas has shown erratic brightness jumps, hinting at buried fractures. The newcomer has remained calm, holding its green glow with surgical precision. If these patterns hold through perihelion, they will become more than data points. They'll become a roadmap for understanding the diversity of interstellar fragments passing through our system. But this competition isn't just scientific, it's human. Observatories have limited bandwidth, missions have finite funding, and public attention drifts easily. In that sense, these two visitors are like overlapping storms, each demanding its own spotlight before fading into the void. No matter how advanced our technology gets, we still live under the old constraint of time. Somewhere in this noise, though, there's a strange symmetry. Two objects, born in different, distant regions of the galaxy, have crossed paths here, around our sun, at the same moment in history. Their origins are silent, their trajectories unplanned, and yet for a brief moment their stories intersect. In a few weeks one or both will disappear into the dark. The competition will end not with a winner or loser, but with silence. But the data they leave behind could define the next decade of interstellar science. For most of modern history, the idea of interstellar visitors belonged to theory, not daily observation. A comet that didn't belong to our solar system was a once-in-a-lifetime event, something distant, almost mythical. But now, in just a few short years, the landscape has changed entirely. Oumuamua, Borisov, Atlas, and now this new green flaring traveller. What was once an anomaly is becoming a population. A quiet, steady migration of ancient bodies passing through our star's domain. Astronomers are beginning to speak differently because of it. Instead of asking if interstellar objects arrive, they're asking how many are arriving each year, how many escape detection entirely, how many carry volatile chemistries that don't match anything we've catalogued before. How many, right now, are drifting through the outer edges of the solar system, unseen, waiting for the moment they light up. This is the population shift. For centuries, human beings looked at comets as omens. Then we came to understand them as local wanderers, fragments from the outskirts of our own system. Now, we're realizing that some of the objects streaking across our skies are not local at all. They're not tied to our star, and they never were. They come from places we will never visit, carrying clues about stellar nurseries we can't see, civilizations of matter that existed long before we arrived. The green flare currently climbing through the inner solar system isn't just an event, it's a data point in a growing curve, one that suggests our skies are more crowded than we thought. The only reason we're seeing this pattern now is because our instruments have finally caught up. Surveys are deeper, algorithms are sharper, Networks of citizen observers fill in the gaps that space agencies can't. What once would have slipped by unnoticed is now being recorded, tracked, analysed, and the more we see, the clearer the picture becomes. These visitors are diverse, but they're not random. Many share the same fingerprints: early activation at great distance, volatile chemistry dominated by carbon compounds, smooth or accelerated brightening curves, and metal signatures that hint at low metallicity birthplaces. It's a story that's bigger than any one comet. It's the story of the galaxy itself, told not through stars but through the silent stones that drift between them. If the models are right, dozens of such objects pass through the solar system every year. Most are too small or too dark to detect, but some, like Atlas and this newcomer, flare brightly enough to reveal themselves. And each one that does is a window, a chance to see not just where we are, but where we are drifting through. This shift isn't just changing how astronomers think, it's changing how humanity sees itself. For centuries, we've imagined the solar system as a quiet neighbourhood, its comets and asteroids our own ancient debris. But the truth is less tidy. We're living in a crossroads of cosmic traffic, and only now are we beginning to glimpse it. The implications stretch far beyond astronomy. A richer understanding of interstellar object populations means more than better data. It means better planetary defense strategies, better early warning systems, and, perhaps most importantly, better opportunities for rapid response missions. If these objects are common, we don't have to wait decades for another chance. We can prepare for the next one. We can meet it, study it, touch it. And yet, beneath the strategic planning, there's something quieter, something almost poetic. Each of these visitors has spent unimaginable spans of time drifting alone through the dark, untouched by stars, unseen by eyes. And then, for a heartbeat of cosmic time, they pass us. They flare green, or burn pale white, or stay silent like Oumuamua, and then they are gone. This new object will be no different. In a matter of weeks, its glow will fade, its coma will disperse, and its name will join a growing list of travellers who passed by and left only a trail of data. But the pattern it helped reveal will remain. The population is real, the shift is here, and the sky is more crowded than we ever allowed ourselves to believe. The era of isolated anomalies is over. We've entered the era of patterns, not just stories about single comets, but a growing, living archive of interstellar messengers moving through our sky. Each one is a line in a language that we are only beginning to learn. Above our heads, the night looks unchanged. The stars are fixed, the darkness familiar. But hidden within that darkness is a quiet armada of travellers, old, cold, and silent. For centuries they passed without notice. Now they are stepping into the light. One after another, they are revealing themselves in the glare of our star, leaving chemical fingerprints for those who know how to read them. This green flaring visitor will pass. Atlas will follow its own path. Others will come. They always have. The only difference now is that we are finally looking, finally listening. And in their silence, these objects are telling us something profound. The galaxy is not far away. It's here, brushing past us, one frozen messenger at a time. Long after this object is gone, the pattern will remain. The sky we thought was quiet was never quiet at all. We just hadn't learned its language yet.